share the content with you. Okay. Last time we have started to talk about skip list, remember? Skip list provides logarithmic time search, insertion, and deletion operations. But this logarithmic time is average logarithmic time. Worst case running time is linear, as we talked about last time. In skip list, we have several lists actually. So we try, for example, for search operation, we try to locate a data element in by looking at several linked lists. So instead of searching a single linked list, we search several linked lists, and we claim that this operation improves the running time. How it happens? We have seen a similar situation before actually. Remember the shell sort. Shell sort performs several insertion sort operations, but still improves insertion sort, right? How? For first or a couple of previous sort operations makes the coming sort operations simpler. Doesn't need to perform from scratch, but the solution becomes more available after each sort operation in shell sort, right? Similarly here, we search the element, data element in the highest level linked list first, and the result of this search operation helps in our search operation in the next level. Next level search operation helps in searching the element in the next level, etc. So after searching at this level, we get some information, and it helps searching on this level, and searching on this level helps for the next level, etc., etc. So that improves the running time from average case linear to average case logarithmic time. Okay. So let me talk about the situation here. The lowest level linked list contains all the elements, right? And the next level, one higher level, contains some of the elements that are at the first level. Second level linked list contains only some of the elements in the first level. And the third level contains some of the elements in the second level, etc. So, for example, both 5 and 10 are available in the first level, but only one of them, 10, is available on the second level. And as you see, 10 and 20 are available on the second level, but only 20 is available on the third level, etc. So not all the elements in the previous level available on the next level. Actually, we would like it to be halved. So all the elements are in the first level. Among them, only half of them is available on the next level, second level. And for the elements on the second level, only half of them is available on the third level, etc. So the number of elements decreases exponentially when we go higher and higher levels. If there are n elements in the first level, we expect n over 2 elements in the second level. And in the third level, we expect n over 2 square elements, and over 4 elements, and fourth level, n over 2 to the cube elements, and over 8 elements, right? So after performing search on this level, we locate some of the linked list in this third level that the element resides in. For example, we know that 35 is between 20 and 40 in the third level. So we do not look for the elements here or here in the second level, but search for elements here for the second level only. So we skip some of the elements from searching when we go down on the levels. That improves the running time of skip lists. Okay, so for any skip list, the we have a level. For example, this skip list has level 4, since we have 4 linked lists, and each element is either level 1 or level 2 or level 3 or level 4 in the skip list. Each node can be level 1, level 2, or level 3, or level 4 in this skip list. Okay, and as I said, number of elements in first level should have all the elements. There are n nodes in the level 1, but in level 2 only half of them on average will be available. I'm saying average since when you insert and delete, the number of elements in different levels could change, and you can have a worst case where level 1 has n elements, but all the other levels are 1 or 0 elements, right? That's also possible, and this is the worst case for the skip list, where the structure becomes like single linked list, since the linked list of these higher levels doesn't help at all. Okay. So we have talked about these. So the search operation starts from the highest level. We search for, let's say, 45. We start with the highest level, and we go to this node 40. 40 is greater than less than 45, so we have to search this part only, and in this part we go one level down, since there's no more element in the linked list. Then we go down again, there is no element in this third level, so we do not do anything but go one level down. And when we look at that, there is one more element, 50, which is greater than 45, so we go one level down as well and find 45, right? So we haven't looked at all these elements to find 45, right? That's the improvement. Okay, we have seen how to search last time, and we have seen this algorithm. We start with the highest level. M is the highest level node. So we start from the head actually at the highest level, and uh, we follow the links at that level, level M, to find the largest value that is less than or equal to target. So the value is the largest value that is less than or equal to target. So it can be equal. If it is equal, we found it, and we do not need to do anything else. If it is less than, we go one level down and continue searching the previous level and try to locate the largest value that is less than or equal to target and the previous level, and continue with the previous until the first level. And the element should be there in the first level if it is available. And if the element is not in the first level either, then the element is not found. If m becomes 0, then the first level is search for the element as well, and still we couldn't find an exit from the loop, then we know that the element is not in the list. Okay, this is the algorithm. As you see in this algorithm, there are several search operations performed here, but these search operations do not start from scratch, from head, but from some value in the middle of that linked list. For example, as I said before, for while searching for 45 in the first level, we start from 40, not from 5. That helps a lot, right? Okay. So at each level, we have fewer and fewer elements. So when we start searching the highest level, we search between very small number of elements. Then we get rid of some part of the elements in the previous level, actually, and the number is almost half. So when we go from one level to other, the previous level, we approximately eliminate half of the elements as in binary search. That's why we have logarithmic performance similar to binary search. Okay. Of course, as in binary search tree, remember in binary search tree with one comparison, we eliminate left subtree or right subtree, but we are not sure how many elements are eliminated. Here, actually, we eliminate some elements, but we assume it is almost a half, but it's not necessary to be half, and we may not be able to eliminate anything, and in that case, we may hit to linear time. This logarithmic performance, as I said, average case logarithmic time, not the worst case. In the worst case, linear time operation required for the skip list. And that skip list is a degenerate skip list as this degenerate binary search tree that we have talked about before. Okay. What about the insertion? Insertion is similar to binary search tree. We first try to find the target value. If we found it, we do not need to do anything. If we couldn't find, actually we search terminates somewhere, and that place is where the new element has to be inserted. For example, when we search for 36, the search terminates at 35. Since when we go to next at the first level, we have 40, and 36 should be available here between 35 and 40, but it is not, so the search terminates over there. And when the search terminates, we know that the element has to be inserted in between 35 and 40. So during search process, either we find a target, and in that case, we don't need to do anything. The insertion, we do not need to insert anything. But if we couldn't find the target, we find its predecessor in the first level, and that is the position to be inserted, that value. So we know that 36 has to be inserted in this position, but we have to determine the level for 36 as well, right? So how many linked lists that 36 should be available inserted in. We can insert only the level 1 linked list, but we can also insert a level 2 linked list, or level 3 linked list, and level 4 linked list maybe, right? So we have to determine the level for the new node. And this level should be randomly picked. Remember, all the elements has to be at level 1, but half of them should be available at level 2. So being at level 1, it should be 1/2. The probability of being level should be 1/2. Probability of being level 2 should be 1/4, which is 1/2 squared, etc. So in general, probability of being at level m is 1/2 to the m. And we pick a random number, random level based on these probabilities, right? And this distribution is called logarithmic distribution. So we pick a random number from logarithmic distribution, okay, to determine the value, determine the level. After determining the level, actually, let's say we have determined the level to be 3 for 36, then we insert 36 into all this level 1 linked list, level 2, level 3 linked lists. How? To be able to do that, we have to know this value, copy in here, and this should be updated to point here, right? Similarly, we have to remember this one, copy in here, and update the link. So we have to perform two link updates for this true, and these links has to be updated, and we have to remember the values of these three links. Okay. So during the search process, we have to record previous nodes of the 36. Previous nodes are had for the fourth level, 20 for the third level, 30 for the uh, second level, and 35 for the first level, right? We have to remember all these values. Of course, we are not going to use this one since it is not in the fourth level, but the rest will be used to insert 36 into all these linked lists. Okay, so we have to update these values to point 36, and 36 has to be updated to point wherever these values are pointing before 36 is here, right? These values are before 36 is inserted. So these values has to be moved to 36 as in here, right? So by this operation, we can end the insertion process. But when we add more and more elements, the number of elements increases, and we have to increase the level for the skip list as well sometimes. Since we say that if the level is m for the skip list, the number of elements n in that skip list should be between 2 to the m minus 1 to 2 to the m minus 1. Okay? If it is not, if n is less than 2 to the m minus 1, we have to decrease the level. If it is more than 2 to the m minus 1, we have to increase the level. During insertion process, we can reach a value number of elements greater than 2 to the m minus 1. In that case, we have to increase the m value, the level of the skip list. So we are talking about level 4 skip list. Level 4 skip list holds between 2 to the 4 minus 1 to 2 to the 4 minus 1 elements. 2 to the 4 minus 1 is 8, less than or equal to n, less than or equal to 16 minus 1 is 15, right? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And 11 is between 8 and 15. That's why we have a level 4 skip list. If we insert 4 more values, 12, 13, 14, 15 elements, still the skip list is level 4, but if we insert one more element, and will be 16, and and beyond that limits, so we have to increment the level as well. So if 16th element is inserted, we have to increase the level by 1 as well. Okay? Or when we delete the elements from this linked list, there are 11, 10, 9, 8 is okay. But if we keep deleting, delete one more, and if n becomes 7, we may need to update the level. Actually, updating level is decreasing the level is not easy. Increasing level is easy. That's why during this deletion process, we do not decrease the level, but during insertion process, we increase the level. So actually, we do not decrease the level during, usually we do not do it during deletion process. Okay, but we have to increase during insertion process, and we are gonna see how we are gonna do it in a minute. Okay, for example, 36 is the 11th element, so we do not need to increase the level. Okay, this is the inner class for skip list node, skip list node class. At each skip list node, we have to keep a data and links for several linked lists. When we create a linked list node, we specify the data and it is level, it's level. So it's gonna be in that many linked lists. So we create m links to for the next node in the linked list, and we have SL node array to keep that linked list, the links, and the data, of course. It has to be initialized during creation of the SL node, right? This is the constructor. Okay. During this search process, as we have said, we have to remember the previous nodes. For example, during the search process of 35, we have to remember head as previous value for the level 4, and for 20 for previous value of level 3, and 30 for two previous values for level 2 and level 1. Okay, and we have to keep this in predecessor array. So we are gonna keep a predecessor array, and that predecessor array will keep the predecessors of 35 at each level. Okay, of course, only in the first level we predecessor links to 35. At the other levels, it links to some value that is greater than 35. Okay. if we are looking for 30, for example, the predecessor would include these values, and for both second level and first level, we are pointing to 30, but still we are sure that at the first level we are pointing to 30, since all the elements are in the first level. Okay, so this predecessor array is the result of the search operation. Actually, we are going to define a private search operation which will return the predecessor array, and we are going to define the public find operation based on the search operation. So search will search the target and return predecessor, and based on this predecessor, we look at the first predecessor value to locate this node, and the first link in that node could be null or pointing to the correct value, or pointing to a value that is greater than the value. So we check the first predecessor and the first link at that predecessor. If it is null, we know that we couldn't find the value. If it is not null, we can compare the value at that node with the target. The value at that node could be larger than target or equal to. It cannot be smaller. We know that the search finds the largest smaller value, so it cannot be smaller. If it is equal, we found it. We return the data. If it is not equal, greater, or if the link is null, we know that we couldn't find the value, and we return null reference, right? This is the search operation, the find operation actually. The search method is in here, which returns a predecessor array, as I said. And as you see here, first we create a predecessor array by using this max level. Max level is the level for the skip list. That's the data member of skip list class. So we just create a predecessor array of size max level. And of course, we have to start with the head. Current is head. We start with the head, and from the highest level down to first level, we have to continue searching. Okay, so I is from 3 to 0 in our case, not 41, since the indices for the predecessor array are 3 to 0. So we go from 3 to 0. Actually, we can get that 3 by subtracting max level by 1, or of course, since current is head, then the links array, size of the links array will be max level anyway. So we can get this value or use max level instead. So in this for loop, we go through all the linked lists, and for each linked list, we perform this while loop, while the link at level I is not equal to null, or if it is not null while it is less than target value, we update the current. So we go forward and forward until we find something that is larger. As you see, if next is larger, we stop at the current. Or next is null, we stop at the current and continue with the previous level. But before continuing with the previous level, we save this current in the predecessor array at that level. So this search operation says the predecessors here for each level and return the predecessor array. Okay. And as I said, this search operation is linear time if we have if other than the head, everything are in the first level, and all these links are null for the head, then actually what we are having here is a regular linked list, since these linked lists are not useful. So in that case, the running time for this operation would be as bad as linear time. So the worst case running time of this search operation is linear. Best case is constant, since we can find the target. Since we have to find these predecessors always, and there are log n predecessors, as you remember here, since n is between these two, then you take a logarithm base 2 log n, and it is close to, let me say this, m. So log n is in between m and m minus 1. So when you take this value, that is actually increased by 1, and take this, it becomes this one, right? So the number of levels is logarithmic. So the number of where am I? The predecessor array is logarithmic size. So if we have to fill up this logarithmic array, so it takes logarithmic time in the best case, and average case still logarithmic time. And we are not going to talk about the details, but average case it's logarithmic time as well. So since this search operation uses find operation uses search, the same running time is applies to find as well, since everything here is constant time except the search, right? And again, for the insertion, we can use this predecessor array. For example, to insert 36 here, we have to insert it into, let's say, 3 linked lists, or 4 linked lists, or 1 linked list. Still, we have to use this predecessor array, as in here, for all the links, all the ith linked lists from for I equal to 1 to 3. In this case, actually 0 to 2, since uh, indices are from 0 to starts from 0, right? We perform these true operations. First, we take the predecessor's link into new node, and the predecessor's link should be updated with new node, right? This order of these true operations is important. We cannot do vice versa. Okay, to be able to determine the size of a node, uh, we should use uh, exponential distributional. As I said, the value of 1 has to have probability of 1 over 2, level 2 is 1 over 4, level 3 is 1 over 8, etc. This code generates this value. Here, the max cap is the maximum number of elements possible in this um, uh, in this skip list. So it is 2 to the m minus 1, right? Max cap is 2 to the m minus 1. So we create a random number from 0 to the m minus 1 here, and increment here 1 by 1, so it becomes to the m. When we take logarithm of this value base 2, this is how we do it. Since this log operation is based e, we divide with log e base 2 to log e base n is equal to log 2 base n, right? This is what we calculate here, and take the logarithm of this value, random value, base 2 logarithm, and we take the integer part. So in that case, having 1, 2, 3, 4, for example, for 2 and 3, we get 1, right? For 4, 6, 7, 8, we get 2, etc. So the probability increases as we go up to levels. So we return this value, max level minus k, since the probability of getting 1 is the smallest probability, but we would like it to be largest probability, right? So we do this. This is a small, to correct a small glitch in this calculation. If k is larger than max level minus 1, we decrement it by 1 to make sure that these values correctly specify the level value. So please go over this algorithm and make sure that you understand. This is the last thing to talk about. So we have to find this level of this node, put in this skip lists, several linked lists. But if the size is increased, over max cap, maximum capacity, we have to increase the max level as well. Of course, when you increase the max level, you have to increase the max capacity. This compute max capacity computes this value. If level is m, the capacity, max capacity is 2 to the m minus 1, as we said. Of course, if you increase the capacity, you have to increase the level, you have to make one more node over here, one more element over here. So this array size has to be increased by 1, and this is done here. So the head links array at head is to be copied into one more element array, right? And links array is updated. This is for the predecessor array. You can do it if the predecessor array is required, but otherwise it's not necessary. So these two are for the predecessor array. I can skip that for the time being. So this is not the whole code for insertion. You can look at the code in the book and make sure that you understand everything for skip list as well for insertion and search process. And as we said, the performance of skip list is logarithmic as binary search tree. As the binary search tree, logarithmic performance is average case performance and worst case performance is linear. But still, the important thing about skip list is it is not a tree. It is a list, and as in vector, it enables concurrent access. If you need concurrent access, it is better to use skip list instead of binary search tree-based methods. Okay. We have already talked about these, so I can skip. I can stop here. It's been 11:20, so our time is up for the first hour. So I'm gonna stop here, and you can ask any questions during the next hour. We will have 10 minutes break, and after the break, you can ask questions about skip lists or ask questions about we are gonna review the questions about the exam. Okay, so I will stop here, and we are gonna have 10 minutes break.